Okay, so now we're going to take a look at all three of the models you've learned this year and try to figure out how you know which is which. Because we've talked about linear, which are lines. We've talked about quadratic, which are parabolas, and now we're talking about exponentials. And oftentimes people gather data and then graph it to see what kind of pattern it actually follows. So we're going to practice doing that. So when you take this and it says graph each data set, which kind of model best describes the data, it's both positive. I have the squeakiest chair in town here. So we have the bacteria here, population. And the time in hours down here. And there's a 4 hours, so I'm going to split this up into 4s. And we've also talked about bacteria, and I look and see, okay, it goes all the way up to 6,000, so I'm going to go up to 7,000. 1, 2, 3, 4, 5, 6, 7. That's our bacteria. All right, so let's graph these 4 points because these are coordinates, aren't they, class? Oops, turned it upright. So this is the coordinate 0, 24, and so on. So we can go here to 0, 24. It's barely above the line, right? Because the first spot is 1,000. The next one's 196, so that's not much further. And the next one's 384. That's still under that 1,000. And then we finally jump up with the 3 to 15. That's in the middle. And then 4 goes, wow, way up here. So we can kind of see, can't we, what kind of a graph we got going here. Looks familiar, and of course I missed that one point, but it looks familiar to the ones we just started learning, doesn't it? It is an exponential pattern. And when you recognize it, it's easier to do some predicting or estimating on future data. Now, lots of people, as you get older and into math, you will be getting graphing calculators. If you have one, you can certainly try to graph some of the data, and it's kind of fun to play around with that and see the different graphs, so feel free. All right, so the next one is boxes and reams of paper. Okay, so we have paper here, boxes, and it's kind of fun too to, if you can think about it ahead of time and try to think of what do you think is going to happen, like with the bacteria, how it's just going to keep propagating, and it's going to just get grow exponentially fast. And here, boxes and reams of paper. What do you guys think? I'm not going to tell you because I want you to think. But the boxes go up to 50, so I'm just going to go by tens. And the reams of paper go up to 500, so I'll go by hundreds. Okay, and now plot them 110. And 550. And 2,200 and 5,500. Is this following what you guys thought? What is it? Looks like a pretty straight line to me. It's a linear function. All right, so just for a refresher, I put the 3 different ways we see an equation. We have our linear, y equals mx plus b. Those are lines. We have our quadratic, which are parabolas, and now we have a new one, our exponential. Okay, so those are the 3 base formulas, general forms of these functions. And in turn, we've learned how to look at data sets and figure out if something is linear, quadratic, or exponential. So let's take a look and see if doing it that way we can figure it out. So I do a double check over here and I see, yep, This is right in line. This is all +1, so we're good. Now over here, is there a difference? So right away I can tell the difference isn't going to work for a linear, right? Could work for a quadratic. But how about, I'm trying to rule out and decide if I need to add or multiply. Does it look exponential? Does it look like I'll be able to multiply something and have it consistently be the same? No, and the reason is right here, right? How could you possibly have the same? So that's not going to work. So the only option here is if it's a quadratic. So let's check it out. All right, so what's the difference? 4 to 68 is a +64, and this is a +32, and this is a +0, and this is a, that goes down, so it's a -32. Okay, so obviously it's not linear. Let's check quadratic. From 64 to 32, it goes down 32. Goes down 32, and it goes down 32. Yes, it did work, didn't it? And some of you might have seen that because you saw the hundreds and then you saw the 68s. And guess what the next one is? Down here, it's probably going to be a 4, right? You can kind of see the pattern here. So yay, that did work. All right, over here, do a quick check here. Yep, +1, +1, +1. Okay, good there. Multiplying. Well, you can check the ratios. Let's try it because there's a hard numbers to tell, so it could be. I don't think the adding is going to work. The difference doesn't look, at least for the linear. It might be a quadratic, which we could check. But let's look at the multiplication. So remember, to get your R, you take the number and divide by the one before it. So let's do that. 1169.86 divided by 1,000. Obviously, that is going to be, that ratio is 1.16986. And how about here? 1368.57 divided by 1.169.86. Oh. Around it. And since these are money and they're rounded, this is probably exponential. Look at that, guys. Yes. It's exponential, and the reason they're just slightly off way at the end is because it was probably rounded. I'm assuming it was rounded here, since it was money. But the ratios were the same. Excellent. All right. One more problem. A little bit shorter than yesterday. I know some of these are a little longer than others. It says use the data in the table to describe how the number of people changes. Then write a function that models the data. Use your function to predict the number of people who received the email after 1 week. Okay, well, let's take a look at what we have here first. Kind of understanding your data. +1, +1, +1. Now, when we look over here, do you notice anything? I see this comes out as times 7, and you guys should see that too, because your multiplication tables should be so strong that you see that. But, you know, then again here, this is bigger. So let's just check. Does 56 times 7 work? Yes. Okay, check the last one. Does that work? Ding dong. We got it. All right. So we have an exponential equation here. And here is our general form, isn't it? Y equals AB to the X. And do you remember what the A was? The A was your first piece of data that you have, your 8. And do you remember what the B was? That was your rate, your factor, your change. What's it multiplied? Your R. Thank you. I couldn't pull that out of my head. Your R. Now, what is it changing by? And then raised to the X. And X would be the number of times. Now this is tricky because if it would have just started with a 1 here, I would just put in, well, it'd be 7 minus 1, right? Where's my original equation? I should just go back and use that one. This is the generic one, but I'm going to go back to this one. I think that's more clear. Let's use, this is the same. It's a times b to the x, but I think this is a little not as clear. So let's go over to this one. So we want to know a sub what? Which number? And we want to say after 1 week, you might want to say 7. But the problem here is if I bring this down, 5, 6, and 7, this is actually not the 7th term, is it? Because this was the first term and it was 0, so it throws everything off. So this is the first term, second term, third term, fourth term, fifth term, sixth term, seventh term. This is my 8th term we're actually looking for. So that's why that's a little confusing. You can't just throw in the 7 there. The first term was an 8. The rate was a 7 raised to the 8 minus 1. So the 8th term is 8 times 7 raised to the 7th power, which is, get this, grand finale, that many people received that forward. Is that crazy? After a week, if everybody forwarded it. So anyway, there you go. I hope you have a great day, and God bless you. Good luck on your quiz tomorrow.